This doesn't work. No? Can I use yours? Yeah? Okay. This is a PDF. Okay, cool. Thanks. Does it have a laser?
Yeah, the middle one is a laser.
Oh, cool. Where does this go? What do you do with that? All right. I'll stand there, I think. Sorry. I'll just put it in my pocket.
Hello, everyone. Welcome back. Here we have Robin Turnbull, and he will be talking about science at extreme conditions.
Hi, okay, so thanks for the introduction. I'd like to start by welcoming everybody to Valencia and thanking the organizers for giving me the opportunity to give this presentation, which, as you can see, is entitled Science at Extreme Conditions. This should be quite a familiar theme because just before the coffee break, Josu, who's a PhD student in my group, was talking about extreme conditions for about 40 minutes. My presentation is only 15 minutes, so we're going to go through quite a lot of information quite quickly. I hope you can see something interesting. I'm going to approach it from a slightly different perspective, so we'll see that in just a few minutes. So we have three main aims of this presentation. The first one is quickly to determine again what we mean by science at extreme conditions. The second aim is split into two parts, the first of which is what makes these conditions so extreme, which is a question of context. Why are these conditions interesting? And then finally, the third and final aim, which is going to be the bulk of the presentation, which is to look at some interesting materials and phenomena encountered in the world of science at extreme conditions. So let's begin with number one. What exactly is science at extreme conditions? I think you should have quite a good idea what science at extreme conditions is. Basically speaking, it's a study of materials and how materials react and change when subjected to extremes of pressure or temperature or large external fields such as magnetic fields or electric fields. I'm an investigator in this department and I'm an experimentalist, and I mainly focus on high pressures, so that's going to be the focus of this presentation. So just a quick summary of the experimental techniques which Josu mentioned earlier. We use diamond anvil cells to create high pressures. You can also use lasers or explosions to create high pressures very, very quickly. That's known as dynamic compression. To create low temperatures, we use helium cooling. And to create high temperatures, again, you can use lasers or electrical resistive heating. And I'm not going to talk about any of the diagnostics particularly, but Josu mentioned earlier we use X-rays and optical spectroscopy. We can also use neutron diffraction to study how the materials change under high pressure conditions. And of course, it's important to mention that very often we complement our experimental findings with computational simulations. Okay, so that was this slide essentially answers this question: what is science at extreme conditions? It's a study of materials and how materials change under high pressure conditions. Okay, so the second aim was to discuss what makes these conditions so extreme. Why do we call them extreme conditions? So pressure, which is what I'm mainly interested in, possesses perhaps the greatest range of all the physical variables. So for example, in the vacuum of space, we have an incredibly low pressure, essentially 0 pascals. The unit of pressure is pascals, PA. Then at the other end of the spectrum, we have incredibly high pressures inside, for example, stars or neutron stars. Here we have 10 to the power of 34 pascals, which is 34 orders of magnitude. And just to give you an idea of the scale of these pressures, this is a 1 followed by 34 zeros. Okay, so obviously these are the extreme examples. We also are interested in everything in between, so we have this logarithmic scale here. Joseph mentioned that in this room, this very moment, the pressure is 1 atmosphere, which is 10 to the 5 pascals. So here we are on this logarithmic scale. The pressure in the center of the Earth, for example, is approximately 1 million times greater than the pressure in the center of this room, in this room, sorry, which would be 10 to the 11 pascals in the center of the Earth. Now, as scientists, as physicists, we are interested in explaining the physical world around us. So it's important to mention that in the solar system, 90% of the matter in the solar system exists at pressures larger than or similar to the pressure in the center of the Earth. So it makes sense that we would want to study materials under high pressure if we want to understand the world around us. This blue region here shows the pressures which we can generate experimentally in the laboratory. So for the remainder of this talk, we're going to essentially zoom in on this area here and look at some of the interesting materials and phenomena which we encounter in this specific range of the entire pressure scale. And I keep referencing Josu's talk. It's because we're in the same group, right? Josu was using the units of gigapascals, GPa. So we do that in high pressure science to make the numbers easier to understand. So 10 to the 9 pascals is 1 gigapascal, or 1 GPa. I'm going to say GPa. So this, in this pressure range that we're interested in is actually between 1 GPa and 1,000 GPa. So we're going to look at some materials and phenomena in this region. But since we have this whole massive pressure scale, I thought it would be useful to say why we're particularly interested in this small region here. So what's interesting in this pressure range between 1 and 1,000 GPa? The key is the energy. So the energy associated with these pressures is relevant to the behavior of electrons in materials. And electrons largely determine material chemistry and material properties. So previously, we saw that pressure is equal to the force divided by the area. And that is correct. But we also know that pressure is equal to the energy in the system divided by the volume. And I think this is really the key, the energy density. Because what we really do when we increase pressure on a material is we increase the energy in the material. We increase the energy density, and we open the possibility to create new materials, which is what's really exciting about this area of physics. So in this table here, since we're talking about the fact that it's the energy associated with these pressures, which is the relevant thing, I've summarized the pressures that we're going to look at, the energies associated with these pressures, where we find them in the universe, and the type of interactions involved. So if we quickly take a look at the first row, between 0.1 and 1 GPa, the energy associated with these pressures is about 1 millielectron volt, which is on the energy scale similar to the weak van der Waals interactions, which I'm sure most of you have heard of. And we find these pressure scales in real life in deep oceans and in comets. Then as we increase pressure to about 100 GPa, the energy increases to 1 to 10 electron volts, which becomes relevant for valence electrons, which are the electrons in the outer shell of atoms. And we find these pressures, as I mentioned, in the center of the Earth. Then finally increasing pressure once again to around 1,000 GPa. The energy associated with this pressure, according to this formula, is around 10 electron volts, which becomes relevant for core electrons, and these are the kind of pressures which we find inside gas giant planets such as Saturn and Jupiter. So this brings us to the final aim, which is to We're going to use this scale here to guide us from 1 GPa to 1000 GPa, and for each of these points, we're going to look at one or two interesting materials or phenomena which occur in this pressure range or this energy range. So, beginning here at the lowest pressure from 0.1 to 1 GPa, I thought this would be an interesting material to start with, methane clathrate. This looks quite complicated, but we can simplify it and make it easier to understand. Methane clathrate has many different names, such as methane hydrate, methane ice, or fire ice. And methane, I'll show you a picture in a second. Methane clathrate is essentially a solid in which a large amount of methane gas has been trapped within the crystal structure of water, forming a solid very similar to water ice. So here, this is the H2O cage structure of water ice. When you increase pressure to 0.1 to 1 GPa on water ice, this cage structure, in the presence of methane gas, the methane gas gets pushed inside the cage structure. And one thing that's important to note here is because we're still at low pressures, or in other words, at low energies, we haven't actually changed any of the chemistry of this system. So the cage structure is identical before and after we insert the methane molecules. It was thought for a long time that this material only existed in the outer solar system, but a few decades ago they found some of this material in deep ocean deposits. As you can see, it's very similar in appearance to water ice, except of course it's flammable because it's full of methane. Okay, so now we take our first step to higher pressures, 1 to 10 GPa. In this region, we experience solidification of the light elements. For example, all light gas molecules, such as hydrogen, helium, nitrogen, oxygen, and carbon dioxide, they condense into highly compressible solids. So this is an example of a simple phase transition. An everyday phase transition which we see is if you want to make ice, you take some water, you reduce the temperature, and it transforms from a liquid to a solid. In this example, we're transforming from a gas into a solid, not by decreasing the temperature, but by increasing the pressure, which incidentally you can also do with water. If you want to make solid water, you can simply compress water at the same temperature. So in this photograph, this is a photograph from of the surface of Pluto. And here we have a mountain range made of solid water next to oceans of solid nitrogen. I just thought this was a really nice example of somewhere in the universe where we actually see solid nitrogen in reality. Okay, so again, we haven't changed any of the chemical bonding. We've just transformed the phase from a gas into a solid. So now we start increasing the pressure again. We go to our third step, 10 to 50 GPa. Now we can start playing with the chemistry because the energy density is much higher in the material. I think you probably know where I'm going with this slide. So I've put here the saturated bonds become less favorable. The saturated bonds are the double and triple bonds between atoms. Here we have graphite. This is the crystal structure of graphite. We have this, it's a very famous structure, you've probably seen it, the layers of carbon in a hexagonal pattern. And when we increase pressure into this pressure region, we form bonds in between the layers, which forms this extended covalent structure. And I don't think anybody will be surprised to know that this is the structure of diamond. This phase transition was achieved for the first time in 1962 using this gigantic machine here. And I don't know if you can see, but there's actually a man standing here. And I think this is a nice illustration of how far the technology has developed over the last 60 years, because this machine is the size of a small building, and we can today achieve the same pressure and temperature conditions in a handheld device, the diamond anvil cell from the previous presentation. Okay, so increasing the pressure once again, we're still in a similar energy region. On the previous slide, we saw essentially the extended covalent structure of carbon. In this example, I want to look at nitrogen, because nitrogen has a very famously strong triple bond between the nitrogen atoms. So 2 slides ago, in this region between 1 and 10 GPa, we said if you compress a gas, gaseous nitrogen, for example, it becomes a solid. Nitrogen exhibits approximately 15 different solid phases, different crystal structures. The first one you encounter when you increase pressure is the beta nitrogen phase. It's the most simple one. then as you continue to increase pressure, the solid transforms into different crystal structures with increasing complexity. In fact, this monster here was the main result of my PhD thesis, which was published 4 years ago. But what these structures have in common is that they all consist of N2 molecules. There's no bonding between the nitrogen molecules. However, if we continue to increase pressure and temperature, we indeed find the N2 molecules start to form polymers. So this result was published only 2 years ago. And in fact, this year, 2020, represents the 250th anniversary of the discovery of nitrogen. So I think it's quite nice that 250 years later, we're still discovering new things about this supposedly relatively simple elemental system. Okay, so now we've made our final jump to the highest pressures, 100 to 1000 GPa. At these very high pressures, obviously we have much higher energy densities, and at these pressures, essentially all materials start to become metal, they start to metallize. So previously we've seen carbon transforming into diamond, we've seen the polymorphization of nitrogen. In this example, oxygen, which we're breathing this very moment, becomes a metal at a pressure of 100 GPa and low temperatures, I believe. This was first reported in 1990. One of two very exciting areas in high-pressure physics right now is the search for metallic hydrogen. This search has been going on for a long time. This material was first predicted in 1935. It has many possible interesting properties, such as superconductivity. And researchers think this material might actually exist inside the gas giant planets Jupiter and Saturn. And it looks like they finally made this material for the first time 2 years ago at the very impressive pressure of 425 GPa. The second of the very exciting things happening in high-pressure science right now is, I think Joseph mentioned it, the search for room temperature superconductivity. They are approaching room temperature superconductivity, but we shouldn't forget about these pressures here. These pressures make the superconductors not viable yet for any kind of real-life applications, but simply observing the phenomenon of superconductivity at high temperatures can be very informative. So just moving on to the last example now. I mentioned that at these high pressures, basically all materials become metallic. You never know what you're going to find in science, and this is a nice counterexample. Sodium, which is a metal at ambient pressure, actually becomes a transparent insulator around 200 GPa. In this image here, you can see this here is the sodium metal. It's a shiny silver color at 120 GPa. And then here at 200 GPa, you can see the sample is transparent, and we have yellow light traveling through the sample towards the camera. Just to summarize the main aims and conclusions, the first aim was to discuss what is science at extreme conditions. We said it's essentially a study of materials and how materials change under extreme conditions, in particular pressure. Our second aim was to discuss what makes these conditions so extreme, and we talked about the fact that pressure has perhaps the largest range of pressures in the universe. Why this was really the key. Why are these pressures interesting? It's because when we increase the pressure, what we really do is we increase the energy density in the material, which opens the possibility to create new materials which exhibit new properties. And finally, the main aim was to take a look at some of the interesting phenomena encountered in the world of science at extreme conditions. We saw the Methane Clathrate, which was the flammable ice, the solid oceans of nitrogen on Pluto, the conversion of graphite into diamond. We also saw the polymerization of nitrogen and the metallization of oxygen, and we mentioned superconductivity. So I appreciate that was a lot of information in a short amount of time. Thank you for your attention, and I will try and answer any questions that you have. Thanks.
So if anyone has any questions, please raise your hand.
Thank you for your presentation. It was really nice. How exactly can you achieve a pressure of 400 GPa?
So I'm going to answer that in two parts. The diamond anvil cell, which is the device we've mainly been talking about, with that device you achieve static pressure. So you increase the pressure and then the pressure is constant, it doesn't change. Like I said, that's called static pressure. There's also dynamic experiments where you essentially smash the sample with a laser or something explosive. In those experiments, they can go to much higher pressures, but the problem is it's not static. You only reach that pressure for a split second. The 425 GPa for the metallic hydrogen, that is indeed a static experiment, but they used special diamonds. So I don't actually have a picture of it, but normally, in normal experiments, we use diamonds with a flat tip. In the metallic hydrogen experiment, they used a special diamond which has like 2 stages to the tip. So essentially there's a small diamond on the end of the diamond, if you know what I mean. It's very, very small. It's something like 5 to 10 microns across. So I think it's called a double stage diamond anvil cell. The answer is essentially you have a microscopic diamond on the end of the normal diamond. Yeah. There are actually higher pressure experiments. The problem with hydrogen is it's very, very soft. So even with normal diamonds, you can achieve pressures like that on incompressible materials such as osmium, which is the least compressible metal. The fact it's less compressible makes it easier to achieve higher pressure. It's not routine to achieve pressures like that, but it's becoming more normal, yeah. I think my record is like 250 or something, so. After that, the diamond will definitely break, and you have to go and tell your supervisor.
Okay. So most of your work is like high pressures. Have you ever tried working on low pressure, like less than 0 Pascal, or like if it has influence on the chemistry or the physical properties of a material, like ultra high vacuum or stuff like this?
No, I haven't. No. Did you just say less than 0 GPa?
Yeah.
I don't think it's possible. You can't have negative pressure because maybe I'm wrong.
No, yeah, not less than 0, but like 10 minus 5 or 10 minus 7, stuff like this.
No, I don't know actually about the area of science. I suppose it is extreme in the other direction. Yeah, I don't know. I don't know. You'd have to have a look. I'm sorry, I can't tell you about that.
Okay.
Yeah.
Thank you.
But you didn't say it, but yeah, I don't think you can have negative pressure, because if you have negative pressure, it means you either have a negative energy or a negative volume, and neither of those things make sense. So I know you didn't say that.
So, if there aren't any questions,
In the case of the metallic oxygen, are those changes permanent or one?
No, when you decrease pressure, it converts back to normal oxygen, yeah.
I wanted to know if they are permanent.
Sometimes there's a hysteresis. So if you increase pressure to 100 GPa and you enter metallic oxygen, maybe you can recover it back to like 80 or 70 GPa, because it's like a slower transition on the way down. But yeah, unfortunately, you can't hold a piece of metallic oxygen. Yeah.
so any more questions? No. Okay.
Okay, thanks everybody.
Well, thank you, Robin.
Okay, because my presentation is very informal.
Abre el micro, el contrario. Bueno,
Yes.
vale, en plan.
Guay, vale, pues al revés de lo que pensaba.
Es que es un poquito antiintuitivo.
El láser, tenía uno, pero vale, guay. Sí, ya está conectado, perfecto.
Y ya
Vale, hòstia. Vaig a donar les notícies. M'envien d'enviat especial. No, res, no he fet res, Manel. Vale, ja està. Hòstia, que raro és això, no? Vale. Tira-li. Ai, hòstia, espera la presentació. No li tiren res. Bueno, però... Això és més divertit.
Well, now we have Jesus Ortiga, who will be talking about the AFM, the atomic force microscopy.
So, hello everybody, welcome to Valencia, and okay, let me see. Nice, okay. I will not talk about high pressure or extreme condition. We are here at normal temperature, normal pressure, all the kind of things. And first of all, I want to apologize for my English because it's not my best skill, but I will try to do the best I know. Okay, I'm Jesus Ortiga. I'm a PhD student of the Unit of Optoelectronic Processes in Advanced Material and Surfaces. And I work in the ICMUP, the Institute of Science Materials of the University of Valencia, like Joshua and Robin. And my research is focused into lines. First, Raman spectroscopy, but it's a little bit complicated to explain that. And I will talk about force microscopy. That is a little bit complicated too, but I think it is more visual. As the title of the talk said, we want to watch the nanoworld. But what is the nanoworld, the nanoscale? The nanoscale is this range of the space, these dimensions that are between 1 nanometer to 100 nanometer. 1 nanometer is you take 1 millimeter and make 1 million of parts, and you have 1 nanometer. So these scales are very interesting because you have the coexistence of classical physics and quantum physics. So it's very interesting for many broad range of fields, from material physics to biology and engineering and all those things, because you can do very little devices. And here you have some examples. For example, these are quantum dots. These quantum dots are made by our colleagues in Castellón, in the University Jaume I. Here you have nanowires, are wires that have some atoms of width. And here you have a nano device. It's a nano transistor. It's made by nanotubes of carbon. And there are some examples of topics that are now researching, but it's not my research, but are famous topics. To start my presentation, I want to talk about the resolution of an instrument in our lab, because IFM have, I will say it later. The resolution of an instrument is it is written here, is the minimum distance between 2 points that can be distinguished as separate particles. For example, if we assume 2 points separate by a distance d, if our system have a resolution that lets you see distance smaller than D, you will have a good resolution and you will see this images from here. And if your resolution is not good, if you had a bad resolution and you cannot see a distance smaller than D, you will see that. I think it's easy. I think everyone understand that. Okay, so to watch the nanowall is not like easy to go to an optical microscope and say, okay, I want to see something, because optical microscopes that I think I am sure everyone here have used this microscope or something like that and see something. But these optical microscopes are limited by the wavelength of the visible light, and this limit is determined by this equation from here, the Aves diffraction limit, and this limit is around 100 nanometers. So we cannot see this small structure. So 70 years ago, more or less, 60 years ago, appears some solutions that were in the electronic microscopy. Maybe some of you know the scanning electron microscope. And then appears the scanning proof microscopy. And here is the AFM. So, well, but what is a scanning proof microscope? No? AFM is atomic force microscopy, is a type of scanning probe microscope, and it's very easy. You have a proof, and you scan all the material, all the surface, and you are registering this surface you are scanning. One of the interesting points of the atomic force microscopy is that you have a subnanometric resolution, so you can see everything in the nanoscale, and then you have 3D information. In other microscopes, you don't have 3D information, because if you have seen somewhere an same image, you cannot see a 3D information. You have a picture, or an optical microscope, you have a picture, but you don't have a 3D information. Here, for example, you have, this is a kind of material that is called perovskite. Maybe one of you know what is. It's a very interesting material that is used in photovoltaics applications. And, well, here you have the information about in 3 dimensions. So it's very interesting. And, well, but how it works? Sorry by the draw, but I think it's very easy, because it works like a blind stick. I'm sure everyone have seen a blind person that is touching the surface of the ground with the stick and say, okay, you have a ground, and you have to overcome that. They touch with the stick and say, okay, I have to pass on this scale. So it works like that, because AFM works like that. I will show you now with the experimental setup. Here you have an AFM. Here you have a cantilever. This is the proof. This is the cantilever, this is the proof, and this is interaction with the sample. And you register the surface with a laser. And this laser reflects to a ray of a photodiode where you can register the surface. It's very easy. I will show you in the... I think everyone see this screen of here, no? Maybe if you can move if you don't see anything. Well, maybe people, you can come from here if you want. Here you have, I don't, epa, joder, aquí. Here you have the cantilever, okay, is the proof that this is a micro AFM, the AFM is very little, but here you have the cantilever. The blackboard will be the array of photodiodes, and here we have the laser that is reflecting to the photodiode. Okay, one thing that I have not said that is very important, the cantilever is always oscillating, okay, and interacts with the surface. So if we come to, sorry, this is, okay, you will see that the cantilever starts to oscillate, and in the screen you will see the laser oscillating, right? So here we have a remnant is oscillating a little bit. We have to wait to have a normal oscillating. That okay, nice. This is a normal amplitude. Okay, we have this maybe. You say you see the surface that I have here is like that, okay? And now sorry, I will write it and it will be better. We have that topography, and we are scanning here. So this is oscillating in that amplitude. Where I put this part, you see the amplitude change. So I can register this change of amplitude, and I say, okay, I have this amplitude, this part on this mountain in the topography. And if I go to this part, a ver que no entra ahora. Okay, sorry. If I change, okay, the amplitude will decrease because I'm here now again. And if I put another mountain, I will have another time an increase in the amplitude. So the AFM works like that. You can register this variation in the amplitude. But AFM is not only see the topography of the samples, because you can see also the well, I have an example, sorry. This is the same material as I have talked about, it's a perovskite. And here you have the perovskite first, you have one topography, and then here we have an a chemical reaction that have occurred in the surface. So if you are here, you have a topography that have highs and lows between 0 and 110 nanometers, and after the reactions have between 0 and 410 nanometers. So you can see the effects of these chemical reactions. So apart from topography, as I have said before, you can see also electrical properties. And this is much interesting, that topography, because you can see electrical properties like work functions, like, well, it's rated with the Fermi energy of the material. You can see the energy of the surface. Well, it's very interesting. And it's a technique that is a little bit difficult, but I have done a simple scheme. I think is easy in that way. You have a reference level here, okay? It's our an energy reference level. And we have two materials that are not in contact. So the surface of each material have different energies. Okay, nice, everything is okay. This is the tip of the cantilever, the proof, and this is the sample that you have to measure. If you put in interaction, in electrical interaction, the tip and the sample, as maybe some of you know, when you put two materials in contact, two metallic materials in contact, or semiconductor, the energy level, the energy Fermi level becomes equal. So the energy of two surfaces will become the same. But now we have a difference of energy between that is different between the energy of energy reference level and the energy of we have before. So we have to find this difference because it's the energy of your surface. So how we find this energy? So we can put a bias, we can put a voltage, and with this voltage, playing with that, we can recover the initial conditions. And if we recover the initial conditions, we are applying this difference. So knowing finding this difference of energy, we can know how energy we need to extract an electron of the material. We need how the surface of the materials behaves when we put light, all those kinds of things. It's very interesting to know which is this contact potential difference. So I have 2 examples more. This is another perovskite. Sorry, but I work with perovskite and I have these examples. Here we have a very plain topography. Is only 0 to 13 nanometers, and here we have an average voltage in the surface between around 850 millivolts. And if we done a reaction, a chemical reaction here on the surface of this sample, we have a topography scale like before that have increased in the height and the mountains, in the hills and hills. I mean, between 0 and 380 nanometers, and the energy of your surface have decreased to around 400 millivolts. So you can register this change, and you can see how the chemical reactions affect to your material surface. And this is very important because if you know. If you have done some preliminary courses of semiconductors or something like that, it's very important to know which is the energy of your surface, because your surface is your device. In semiconductor physics, it's very important, the surface. So we are always working with the surface. And here you have the change. And for example, another kind of things that you can see, this is the same surface that I showed you before, but we are not we have not made the chemical reaction now. We did later, but but first we have irradiate with a laser the surface and photogenerate carriers. So you can see how the carriers are around these little mountains that you have in the material, and here we switch off the laser, and more or less you can see how with the time the carriers will redistribute in all the surface, and you don't have these concentrations like you have when the laser was switched on. So you can see the dynamics of the carriers in a surface. So it's interesting, for example, in a photovoltaic applications and these kind of things. And this is what my talk. This is my group. This is Ana Cross. Is and with this is Nuria Garro, and both are the leader groups of the leader groups of my group, and I'm the PhD students. And thanks for your attention, and I will try to answer your questions.
Any questions? No? Okay. Well, I wanted to ask you, you've talked about the microscope and everything, and do you have this microscope at your laboratory, or do you have to?
Yes, atomic force microscope is a very, I don't know if very common, but it's usually you can, here in the University of València we have two we have one in the ICMOV, we have another one here in the STIE, are more or less, the whole microscope is like that. I mean, it's very tiny. So you can have in your lab, but you have to, you need a special table that is, that avoids that the vibration of the ground, or maybe, for example, you have seen the tranvia out the university. These vibrations affect to our measurements, so we have to take, we have to have special conditions in the lab. But well, see, yeah, you can do it. You can have it in the lab.
Thank you.
You're welcome. So.
Do you know how to put this on? It's a
Enough time.
okay.
But this. Okay.
So it goes over your
I
ear.
guess I can also connect the computer. Okay.
It goes like this. All right, over your
We
ear.
can do that actually.
If you want to put it
No, we
your
can
side
just
here.
do with the HDMI cable.
Okay.
And I wanted to ask you, how do you pronounce your name?
Kevon.
Kevon?
Yeah.
And the surname? Kevon.
Kadiwala. So again, I will try to put this on this. Yeah.
Over your ears.
Yeah.
Yeah, like that.
Okay.
So you will need an HDMI cable.
Yeah.
Let's turn this off because I'm worried about the batteries.
Okay. Uno, dos. Okay.
Okay.
And how? Oh, sorry. Forward, back. This.
It's already configured. Just keep it in your pocket or something.
This.
Oh, yeah.
Okay. Yeah.
It's, I think, this is the
Yeah.
laser. Yeah, this is the laser. And
Yeah. Not working.
Okay, well, some technical difficulties. Now we have Kevon Kadiwala, and he will be talking about epitaxial growth of mechanism for thin films. Thank you.
Okay, so good morning, everyone. Thank you for joining us here. So I will be talking about epitaxial growth mechanism for thin films. And as in the previous presentation, we saw a lot about AFM, which is a method to do surface morphology for the thin films, actually. So it was really nice that we had that presentation just before this, because in this I will just mention those names. I will not talk about any method, how we measure these thin films, how we distinguish their morphology, their chemical characteristics, or anything. I will be talking only about how this mechanism actually works, epitaxial growth, because this is a new field that is growing, and it's quite hot topic right now, because as also mentioned in the last presentation, perovskites are also being grown with epitaxy. And if you remember from the presentation, from the previous AFM images, they had many bumps. With epitaxy, we can minimize them as much as possible, like we can make them very smooth films. So let's begin. What is a thin film, first of all? So a layer of material which has thickness of from a few nanometers to few microns is called thin film. Anything more than, I would say, like there is no a written in stone definition for that. Like up to this, 2 microns is thin film, and after that is thick film. There is nothing particular about that, not specific. So up to 2-3 microns, from my personal perspective, I would say it's up to that amount is the limit of thin films. After that, I would not consider it a thin film, but up to few microns is considered a thin film. So few nanometers to few microns. And just for reference, a human hair is 100 microns. So we are talking like approximately 100 times thinner than a human hair. That is a thin film. So where do we even use these thin films? So there are semiconductor devices, like in our phones, like our phone have these chips which are very thin. They have thin material, LEDs, optical devices, biotechnology, and many more areas there where we use thin films without even knowledge to general public. So how do we first of all deposit these thin films as well? There are some chemical deposition techniques, there are some physical deposition technique, and there are also some other methods which combine chemical and physical deposition techniques. So for chemical deposition, we have chemical bath, atomic layer deposition, chemical vapor deposition, MOCVD, commonly known, metal organic CVD, PECVD, plasma enhanced CVD. And for physical deposition, we have thermal evaporation, which literally is thermal evaporation of a material. We literally just heat the material and deposit on the substrate or target material. And we have magnetron sputtering, which would require a separate presentation, how it works. Pulse laser deposition, it's quite straightforward, I would say. You just you just heat the target material that you want to deposit on your substrate with very intense laser. You increase the temperature in very short period of time, and you get the material from the target to your substrate. It's literally heating your target material with the laser. So that is pulse laser. You go with pulses. So that is the physical deposition technique. And then there is molecular beam epitaxy. Again, that would require another presentation in itself, but it combines chemical and physical deposition phenomena, let's say, in some sense. So that's why I put it in the middle of that. So now what we know that what is a thin film and how do we make it and what are their applications roughly. So let's get to the epitaxial growth. So as you can see on the image on the left side, epitaxial layer and seed layer. So seed layer is what we have as a substrate, and it has to have some crystal structure. It cannot be amorphous. So that is one condition that we have to provide for the epitaxial growth. So once we have a seed layer, a substrate with a crystalline structure, we can use that crystalline structure to guide our material that we want to grow in that same form or similar form as a layer, which will have similar crystallography as the seed layer. As you can see, it is exactly similar in this image, which is very ideal situation. It doesn't happen. It happens rarely, actually. So this is the basic basis of epitaxial growth. You have a seed layer, and then this seed layer guides the growth of this epitaxial layer through the crystallographic bond, because they have very similar crystalline structure. You have to provide that seed layer according to your material that you want to grow on that. So here is an example. Silicon is on the bottom part and aluminum is on the top. So this is a TEM image, transmission electron microscopy. You can also search about that. That is a separate thing. But this is an image on atomic scale. The scale should be here. It's just 5 nanometer. So this is quite good how to say this, characterization technique. I would say that you can check atomic layers, and each individual line is showing atomic layers. So you can see on the bottom part, silicon has these lines which are parallel to each other, and then you also see aluminum lines which are parallel to each other. And because of that, their natural crystalline structure of being this parallel and having 111 this crystalline Miller index, that is another thing. They can grow on top of each other. So here we have used silicon, and you can grow aluminum on top of that, and it will grow epitaxially. So it will make a crystalline structure directly. You don't have to do. So this just silicon will guide aluminum to grow in this layered crystalline structure. That is the beauty of epitaxial growth. And where the problem lies is how do we find out which material will grow on which material? That is the thing that we have to figure out as researchers. So there are some other things as well, because this is the ideal situation. It doesn't happen very commonly. It happens rarely. Mostly you will have some compressed or elongated bonds because they will not match the seed layer. Sometimes the crystals have bigger space between the atoms, or they have smaller space between the atoms. So they might have to be compressed or strained. And then you will have some stresses in the material that you have grown, the epitaxial layer. So that is called compressed or elongated bonds. And sometimes that compression or the stress is so much that those bonds even break. And here you can see one atom has no connection to the epitaxial growth, because that atom is so far away from the neighboring atom that it cannot make any bond with the material that you are growing. And that is the relaxed lattice, actually. So when the compression gets too much, it will break the bond by itself. And when it breaks that bond, it becomes relaxed. So that is called relaxed lattice. So once we have, in ideal case, we have completely matching lattice, so it matches perfectly. Then we have some compressed and elongated bonds, and then we have some dislocation, which creates relaxed lattice. And then there is the other thing, how this epitaxial material grows actually from, let's say, by layer, because we are growing layers here. And this gray area, the gray part is the substrate, which is the substrate, as in it can be silicon or anything else, any other substrate. And what we are trying to grow on that is the blue layers are the epitaxial layers. And when we deposit, let's say for example, we take here pulse laser deposition technique. We are depositing material by ablation of the target material. If that material is getting absorbed by the surface of the substrate in equal amount to the absorbent by the material that it has been grown. So let me simplify again. If the material that we are growing, which is the blue layer, it has the same absorption capacity as the substrate, then it will grow uniformly. But if you have more surface attraction from the material that you are growing, as in you are growing some material, let's say you are growing aluminum, as we saw in the previous slide. Aluminum has more attraction towards itself, then it will start to grow in a pyramid shape. It will make pyramids on top, like it will make a layer, and it does not want to grow on the silicon because it prefers to grow on itself. Then it will start to make triangles because once it makes the layer, it doesn't need anything. It doesn't want to grow on the silicon, so it will just grow on itself. Then we have the pyramids. We don't want that. That is not the ideal situation. And then there is some situation where there is intermediate forces playing. Sometimes the attraction is higher, sometimes it lowers. So you have mix of both. You have layers as well as some pyramids. And here you can see some actual images of tungsten diselenide on the silicon oxide substrate. The pink part is the oxide where there is nothing, but the purple, light purple, not light, but purple area, it's where the monolayer of tungsten diselenide is. It grows and then it prefers to grow on itself. That's why it starts to make this triangle on itself, and it doesn't prefer to grow outside. So here we have the problem of in the middle, it's called Walmer-Weber. Absorbent surface is, it has, the surface, the silicon oxide has less attraction for the tungsten diselenide to grow than tungsten diselenide itself. So this is not the ideal situation, but it happens much more in real life. So real life, we have many more problems. So what do we do with epitaxial heterostructure? What are the application of epitaxial growth? So in electronics, people have made this tungsten disulfide and molybdenum disulfide heterostructure for various purposes like FET, high performance. But when you make it just with normal, you make tungsten disulfide and molybdenum disulfide on separate substrate and then transfer on each other, it has many defects and it does not perform as well as it could. But if you use epitaxial growth, you grow it on top of each other, then you have very high performing FET devices. Same goes for optoelectronics as well. For tungsten disulfide and tungsten diselenide, if you grow them separately and then you transfer on each other, it doesn't work out very well. But if you grow them epitaxially, you can have nice photodiodes as well. These are very, I would say, current topic of research. So this is not something that is already out for application for the common use. And then there are this photocatalysis, as well. It was mentioned before that hydrogen is a quite good source of energy. So we are trying to split the water as much as efficiently as we can. So there are these things as well. So non-epitaxially, we have this random structure, and like on one place you might have more material, and other place it has very small material. But if you follow epitaxial growth, you will have uniform distribution of the material growth, which is always nice to be able to control how the material is growing. And then we also have electrocatalysis. As you can see, it's the common theme here. Molybdenum disulfide, if you just deposit platinum on it, it will not grow epitaxially, and it will have some different problems with adhesion and as well as some uniformity as well. But epitaxially, if we grow it, it will grow much better, and it will give us enhanced electrocatalytic devices. So then there is this other aspect of epitaxial strain relief layers, as we call it, because there are so limited pairs you can combine with each other that, let's say, one cubic structure, there is one cubic structure of crystal. You cannot match many structures with that specific cubic structure. But let's say you want two materials to grow on each other, but they are not compatible to grow on each other epitaxially. So there is something called graded buffer as well. So here is just literal engineering from, let's say, theoretician as well. You have to work a lot with theoretician here in this topic. And then you can predict if you grow a material. Here we have India INP. It does not match very well with indium aluminum arsenide. So there we have graded buffer. It works very complicated way. I wanted to keep it simple, but I could not find the simpler example for this. So how it works is, let's say you have a gap between two atoms of, let's say, 10 angstrom, just for example. But it does not match with the material that you want to grow. Let's say the target of your material is 5 angstrom. So how do you provide for this extra 5 angstrom that you have on your seed layer? So we reduce that amount of the atom structure slowly. That is called graded buffer. So first we go to 9 angstrom. It will be strained layer. It will have stress in it, but then we grow again on top of it. It will have 8 angstrom. It is strained again. Then we grow on top of that. It will get strained again, and then we strain it, and then we have on top a compatible layer. So there we can. So that method of growing epitaxial films is called strain relief layers. That's how we use buffer layers to grow something that we cannot grow normally. This method takes a lot of work on the theoretician part as well as on the experimental part. Like the people who grow the materials are sort of called growers. Then there are people who work on devices are called device makers. And then there are theoreticians. Here you have to work with like everyone. So there is also another aspect of epitaxy called remote epitaxy. This is something that is just coming into light of this new topic of research. That previously, as we saw, you have a seed layer, and on top of that, using that seed layer, you grow material following the same crystalline pattern. And it was believed that it has to be direct contact, but if you just put graphene there, you don't have direct contact, but still it will grow epitaxially. So we get a substrate, put graphene on top. I am assuming everyone knows what is graphene, the monolayer of carbon. Then we grow our material epitaxially, and then we use the handling layer. It's just some resist, organic resist, PMMS or PMMA or AZ resist used in photolithography. You can use that and use that as handling layer. Peel it off, literally with mechanical force, you peel it off, and then you have your epitaxially grown layer, which is pink, and then you can just deposit it anywhere that you want, on any substrate. And then you have your substrate with graphene, again, ready to use. So this is a reusable method for epitaxial growth. And also this freestanding films, you can remove the handle, this resist by chemical process, and then you have just this epitaxial films, and you can stack them on top of each other like perovskite materials, and you can have very exotic phenomena who are very nicely working for the quantum wells and quantum devices and everything. That goes much more in advance, I think. It also works for nanowire as well. You just have graphene layer, you peel off the nanowires, and your substrate is ready to use again. So this is something that has two benefits. You can reuse your substrate, and you can have your layers to deposit physically on other substrates. So I guess this was complicated enough to give you some thoughts. So thank you for your attention, and I think you will have many questions, so you can also email me and ask me here as well. So thank you for your attention.
So, any questions?
Thank you for your talk. You said that aluminium grows on itself. Why
No,
is
it was just an example.
Oh, right.
I was just using that as an example because actually tungsten deselenide I should have used that as an example, because on the previous slide it does not prefer to grow on itself. It actually prefers it can grow on silicon as well. So epitaxially it can grow on silicon. But at the moment I could not think of this tungsten deselenide, and I used any example I could think of. But yeah, tungsten deselenide prefers to grow on itself.
Okay, why?
So, yeah, so there are these things, as I mentioned, this lattice structure. So it has to match where it is going to grow. If, let's say, this thing, these squares, as you see here, they have different dimension for tungsten deselenide and silicon substrate, it will not grow there. It will prefer to grow on itself because it will match very easily on this. But if you have your, let's say, this silicon oxide is this and tungsten deselenide is this, you see there are some dislocations, and there is also some strain and compression as well. So it will not prefer to grow there. It will just prefer to grow on itself. So that is something you have to deal with, and it goes much more in detail, because for that you should not use pulse laser deposition, magnetron sputtering, anything, but you should go for MBE, molecular beam epitaxy. But that is a separate presentation, I would say. So
Okay, thank you.
Thank you for your presentation again. In this slide, actually, I have a question. In the unstrained relaxed lattice, can you have the opposite case where the distance between the new atoms is smaller than the seed layer?
yeah, so this is the strained lattice, I think. So you are talking about here as well, right?
Yes.
So here, as I have written here, it is relaxed, but it cannot, sometimes it is not completely relaxed. So it might have the smaller crystalline structure as well, which will be still strained, but it gets relaxed from the extreme condition. So I guess that answers your question.
It's because there some bonds break because the distance is higher.
Yeah.
But can you have, can it be formed new bonds from one single atom to two of the new?
No, it will not change its properties for this epitaxial growth. So if let's say, for example, there is an atom of tungsten and it makes only 2 bonds with selenium, for epitaxy it will not make 3 bonds. I think that is your question, right?
Yes,
so
it's like that. Then a bond is broken. But
yes. So it will remain as dislocation. So there will be, how to say, you can consider it as an impurity. It is not as good as this is the best thing. This is okay, and this is something we try to avoid. So yeah, so it is not the best scenario when you have dislocation, but we can work if this dislocation is just happening on one layer, and then we have epitaxial growth. As you see, like second layer, third layer are very uniform, and they are all connected nicely. So we can also use that in some conditions as well. Sometimes we also have these dislocations up to 2 layers or 3 layers, and then it starts to grow normally. So that is also something that happens in epitaxial growth. So yeah.
Thank you.
Yeah.
When you were explaining the epitaxial growth, you mentioned cases where the material prefer to grow in itself than in the surface, or that is equal distributed. There are some cases where it prefers the surface than itself. There exist some cases like that.
Yes, so I cannot think of any material that would not prefer itself. That is always either it is equal or it is less. So any material, let's go back to this again. So any material that is by itself is providing itself a seed layer because it will match very easily on itself because it is itself. But to match it with the seed layer, which is, let's say, some substrate, it will never have more absorption, like more attraction to the substrate that you are trying to grow on that. So either it will be equal or less. So I think
that is, thank you.
Yeah.
So anyone else has another question? No? Well, in that case, thank you, Kevin.
Yeah. Thank you.
So, no vaig presentar-vos encara, no patiu. Que apague que desconnecte l'ordinador del... Ah, sí? Bueno, pues the Physical Way. Quins? Tires ja? Bueno, és igual. No, la guarda igual, això diu que no la guarda i ja està, no passa res. Collo.
Però li guarda el correu, que és el que voleu fer.
Ah, però no passa res, no passa res. No, apagar les pantalles para que no se veja el drive de Ana, pues és igual. Okay, so we have scheduled some more hardcore talks sometimes, and then some other stuff, right? So things like this. So it's my pleasure to introduce these two persons, Ana Garrigues and com te deien? Carmen Galotto, who are going to tell you about something. Well, those of you who are studying physics, you may already know. Those of you who are planning to study physics, you already don't know. Anyway, pay attention. Whatever they do, it will be fine. So you will have fun. So enjoy the talk. And after this, we end today, and we'll see tomorrow.
Espero. No va.
Good afternoon. As Manel said, we're Ana Garrigues
and Carmen Galotto.
And we're going to try and answer the lifelong question, what can a physics student do outside the library?
Even though it will be a hard question to answer because it's difficult to find one outside the library. So first, we wanted to ask especially those of you who still aren't studying the degree, when talking about studying a physics degree, what comes to mind? What are the first ideas that you have?
Don't be shy. Anything, it's okay. Okay, so we're hearing that when you study physics, you think that you only can be like a researcher or a teacher at university, but maybe there are some other paths, no?
Yeah.
Any other ideas? No? Okay. No, those things are the ones we are thinking about.
Say it out loud, please. Okay.
Okay.
We're also thinking about maybe some abstract ideas, like what feelings come to mind when studying physics.
We're not talking about career paths.
Say it out loud, please. Depression, okay.
There. We want to arrive there.
Any PhD students in the want to add something? Nobel Prize, okay, not so bad idea. So what do the pharmacy students think about studying physics?
It's difficult, it's easy.
We cry, okay.
So following this idea, last week we conducted a quick survey among our fellow physics students via Twitter, and these were the main ideas that appeared in that survey. You know, we see anxiety, frustration, effort, satisfaction, vocation. These are the main topics, and well, there are some like more positive and negative, but we see three leitmotifs. The first one is that this is not easy for anyone. This is related to the fact that frustration, anxiety, and the effort is something that is generalized among every student. Then it's obvious that we need support networks, companionship, solidarity, and friends to keep up with this pressure and this anxiety, effort, etc. So we need also motivation and feeling heard, and this here comes the vocation and curiosity.
And here come extracurricular activities into play, which is what we are going to talk about mainly. So when talking about extracurricular activities, it's interesting to ask ourselves, what can an extracurricular activity provide us? Why should I decide to invest my time in that activity instead of in the library? And from our experience, we find that when participating in this kind of activities, which we will go into depth lately, you can meet fellow students, which is really important to build that support network that we were talking about, and not only students for your degree, but maybe also from other degrees, and maybe also master students or PhD students, and even advisors who can teach you and they can help you with their experience. Then there's also networking, which is basically a fancy word for meeting professors and meeting people outside your inner circle to get to know what they do, what they study, etc. And then there's also the possibility to learn outside lectures. I'm sure that most of you are used to the standard way of learning, which is you have a professor here and they are talking about whatever, but you can also learn visiting a laboratory, or maybe even taking part in a conference, not only as an attendee, but also giving a talk. And then there's also the chance to learn some transversal skills, like talking in public, or maybe doing divulgation, which is an interesting skill. And then participating in these activities gives you lots of opportunities, like getting in touch with people that you wouldn't meet if you wouldn't get outside your comfort zone.
So now we'll have reformulated a little bit the question, what can a physics student do here at the Universitat de València? We're going to talk about three main associations, which are ADR, Fotonets, and Espectre Visible.
So first, we want to talk about the ADR, which is the Representatives Assembly. This assembly is formed by the students' representatives, and they are elected by the students. You can opt to become a part of the ADR, and there are two main purposes. Official purposes are keeping students up to date with what happens in the university, anything related to them. For example, when we had the COVID epidemic, they were the responsibles for telling us what was happening, what could we do, etc. And then also they have the task to defend our rights institutionally. They go to meetings with professors. If there's any institutional problem, they will take care of it. But they also have some non-official business. Here in our faculty, they organize carnivals. I don't know if you can see the picture, but these are some of our students dressed up as here. I think the theme was Disney, and honestly here I'm not sure. And this is one of our professors, Maria Jesus. So they also organize leisure activities, and then the faculty dinners, which here are very important. They always tries to organize social activities for the students, because studying a degree is not only going to uni, but also building important connections. And the ADR always makes sure that we enjoy this experience. And then they also organize some cultural activities. They have organized lots of talks and contests centered around physics, but not only around physics. We had a narrative and a writing contest, and then there's also the Cultural Week, which they organize lots of things. They organize talks with PhD students, also talks with all the departments from the faculty, so we get to know what they work in, what research is being done here at the uni, and all of that. And then we will talk about Espectre Visible. This is the LGBTQ+ association here at our faculty. Its main purpose is creating a safe space for LGBTQ students and professors too, but it's mainly focused on students because it's formed by students. They also focus on outreach of LGBT scientifics. They have organized activities to promote the work of LGBTQ scientists, not only like past scientists, but also actual LGBTQ scientists. And they also participate sometimes in the creation of inclusivity policies, making sure that our institution is inclusive and thoughtful of everyone.
Last, we'll talk about Fotonets, which is a student chapter by Optica, formerly Diosa, and is formed by degree, master, and PhD students. So here we see like that every student from first of degree till PhD is included, and they organize visits to our research labs in optics and photonics, and do outreach at the schools and university level. Some of the past activities were conference cycles, roundtable. For example, the one we had here for the International Day of Girls and Women in STEM. Also participating in congresses and science fairs like Experimenta or the National Optics Reunion here in Spain. And as I said before, visits to research labs and outreach activities at school.
Okay, so to summarize, we would like to say that you cannot break the laws of physics, but the laws of physics can break you. So when studying them, it's really important to not only focus in the academic side of your education, but to participate in other activities to take care of your well-being as a student. So that's all, and if anyone has any questions.
I forgot to say that they are third-year students. Well, yeah, so they know what they talk about. And I would like to say that this advice is good for professors too. Yeah. Questions, comments? Any experience in your home universities that you would like to share in this sense, or you don't do anything there? Daniel, just a second. You have to travel.
Hi, I'm a PhD student. I just wanted to mention that there's sports activities too, not only social activities, because sometimes people forget that. I mean, we are freaks, but we also like to do sports too. So you have these social, cultural activities, but there's other stuff that is not mainly organized by the Faculty of Physics, but you can meet other people from other degrees in those activities too.
Yeah, we decided to center the talk about programs that are not supported officially, but the faculty or the university. But yes, Daniel said, there are sports and there are also other activities, like here in the University of Valencia, there's the Entre Iguals.
Valencia.
University of Valencia. There's the Entre Iguals program, which I suppose if you are from other unis, maybe you don't know, but older students like ourselves get in contact through the university with new students, either first grade students or sometimes Erasmus students too, and it's a way to introduce the new students to the university through a same level, not through a professor or someone older, but Entre Iguals in Valencian means among equals. And that's another way to participate in your community too. And there are sports, and I think the university also organizes language courses. There are lots of things you can do outside the lectures.
I just wanted to add that the faculty officially only organizes torturing activities.
Well, and following what Carmen was saying, it's important that all these activities are among equals, because, for example, Photonets, at least for me, has allowed me to participate, for example, exposing a poster in a congress as a third grade degree, year degree student, which I think is not usual, but has gave me that opportunity. Also, the opportunity to go and see other schools and labs, for example, at the CSIC in Madrid, or yeah.
Creo que sí, que si no, no te escolten en el streaming.
I just say sports, but there's some stuff related with art, like music, theater, so it's not only that. I mean,
Yeah.
I was just mentioned one of them. But
Yes, well, as you are mentioning it, the university organizes many things. There's here in Valencia La Nau, which is a side of the university, which organizes theater representations. And also there's like La Mostra d'Art Públic, which organizes a public art exposition here in campus. And its main purpose is to bring the art closer to STEM disciplines. So yeah, there are a lot of things you can do.
Well,
if that's all, thank you for your attention. Pues si no valen dir res.
Sure, you don't want to say anything? Okay, fine. So yeah, okay. So well, we'll convene tomorrow at 9:30, I think, and yeah, and yeah, hope to see you all, right? So yeah, see you tomorrow.